Swayam Prabha. Digital India. Educated India.
Okay, so here's another kind of thing you would encounter. Suppose you want to prove a statement of the form there x is x such that p of x holds. Well, in this case, you can actually prove by example. You can give, all that the claim is stating is that there is some x. So just show one x such that p of x holds, and that's a proof. Okay? As an example, if that statement P here actually has a form P implies Q, then all you need to show is find some x such that Px implies Qx holds. And one way of doing that is find an x where this is vacuously true. If Px is false, then you're done. Right? So when somebody says their x is x Px such that Px implies Qx, one way that statement could be proven, or one way that statement could turn true, is because there is some x such that Px is false, and you can prove it just by finding that x. Or you can prove it by finding some x where Qx is true. In that case also Px implies Qx is true, and so all you need to demonstrate is one x where Qx is true. Of course, it may not be possible to or easy to show either of this, but still there may be a way to show that there is some x where one of these two things holds, right? Either Px is false or Qx is true. Without figuring out which one is actually true, you might be able to show this. And finally, I said this is one way to prove the statement, or even here when somebody says their x is x Px, one way to prove it is to demonstrate an x. But there are several cases where we don't know how to pin down a single x where Px is true, yet we will be able to make some non-constructive argument. It's called existential proofs, where we actually show that their x is an x without ever actually figuring out a single example where it is true. Okay? But in the more general cases that or most common cases that you would come across in this course, when you are asked to prove this, you might actually be able to find a particular x for which the predicate Px holds. A very related, in fact almost the same kind of statements is a negation of a for all statement. So remember earlier what we saw was their x is x Px, and this one is a negation of for all x Px. Why do you say it's almost the same thing? Because this is equivalent to saying their x is x not P of x, right? So it's essentially the same thing. Instead of working with P, you're working with the negation of that predicate. So again, you can prove it by giving an example such that Px doesn't hold, right? So this kind of a proof, when you want to disprove that for all x Px, you're giving an example x such that Px does not hold, is termed a counterexample or proof by counterexample, right? So to prove or disprove somebody claiming that for all x Px holds, you demonstrate a counterexample to their claim. So that is proving the negation of their claim. Here is a quick example. So suppose the claim is that all odd numbers greater than 1 are prime. So somebody just sat down and looked at, okay, 3, 5, 7, oh, that's all prime. So all odd numbers greater than 1 are prime. How do you disprove them? So you need to demonstrate some integer which is odd and greater than 1, as well as it is not prime, right? So you need to show there exists an x in this set of odd numbers greater than 1 which is not prime. And all you need to do for that is show a counterexample like 9. or 207. So anything will do, right? Any one example would do. Of course, if they claim that there is at most one odd number greater than one that is not prime, your counterexample would be to show two such numbers, and you'll have to show 9 and something else, 21. Okay, so these two kind of cases were nice and easy to prove in the sense, hopefully, in the sense that you have to just give one example to establish the truth. But here's another kind of statement which seems harder. It says for all x px. Okay, so now to prove the statement, you have to show that every x in the set, and that set, remember, might be infinite, px holds. So there is no general rule how you will be able to prove this, but here is what structure of that proof would look like. You would start off by saying, okay, let's pick an arbitrary element x in the domain of this predicate. Then we'll work hard and prove that px holds. But in this entire proof, you are not using any property about x. That's not true. So you're saying x is an arbitrary element. So whatever you're saying about x should hold for every element in that domain, right? So no matter what x could be, your proof should work for that x. And then at the end, round off your proof by saying, look, what I just now proved is for an arbitrary x, therefore the proof applies to every value x in the domain, and hence for all x px holds. Okay, so this is what the structure of that proof would look like. In the previous video clip, we already saw an example of this where you are proving a statement of the form for all x, I think it was x is odd, x squared is odd, right? And you would prove this by taking an arbitrary odd number and then looking at its square and saying, oh, that should also be an odd number. Right? So this is a general template for those kind of proofs. Here is another example that fits into the same template. Suppose this px has the form qx implies rx, right? So it's again, for all x something. It's just that something has a little more structure in this example, and so everything else stays the same. It's just this part where you have to prove px holds. Now you have to do it for this particular statement, qx implies rx, for an arbitrary x. And you might start off that proof by saying, suppose qx holds, and then make a bunch of statements until you hit. A word of caution here: in this kind of statement, you are not proving for all x qx implies for all x rx, right? You're proving that for every x, if qx then rx. That's why it fits the template here for every x, px. So once you pick your x and you're going to prove qx implies rx for that x, you get to assume only qx holds for that x. You don't get to assume qx for every x, right? So that's an important thing to bear in mind when you're proving these kind of statements. Okay, so the last template I want to show you is proof by cases, okay, or case analysis. So you can break up your proposition or your situation into various cases and prove your proposition in each case. So for instance, to prove Q, some proposition Q, you could consider various cases. So you first show that one of these three cases holds. So either C1 or C2 or C3. So there are three propositions corresponding to three cases. At least one of them holds, maybe more than one holds. You don't mind. And in each case, you separately prove that, if C1 is true, then Q holds. If C2, then Q, and if C3, then Q. And once you've proven these three these three state propositions separately, you have actually proven that C1 or C2 or C3 implies Q. Okay, and that's just an equivalence you can convince yourself of. C1 implies Q and C2 implies Q and C3 implies Q is the same as C1 or C2 or C3 implies Q. And then you can deduce, since you have already proven C1 or C2 or C3, you can deduce Q from this. Right? So this is just case analysis where you've shown one of these three cases must hold, and in any case, no matter which case holds, Q has to hold, therefore Q holds, right? And yeah, so this last step here, the derivation is, you're saying the C stands for C1 or C2 or C3. So C and C implies Q. So together from that you can deduce Q. Okay, you should convince yourself of that. And same thing works if, sometimes you will do a different kind of case analysis. So you're supposed to prove P implies Q. So remember, in this case, you could start off by saying suppose P, and then you break up into three cases after that. So if P holds, then there are these three possible cases, and then you go ahead and the rest of it looks pretty much the same, except that your final conclusion also has if P, then Q. Okay. Here is an example you might have already implicitly worked with, and this is when we were proving equivalences of logical formulas. So here, for example, I want to say show the distributivity property that OR distributes over AND. So this formula is equivalent to this formula. So remember, an equivalence of a formula is essentially a shorthand for saying no matter what values you put in for P, Q, and R, both sides will evaluate to have the same truth value. So for all values of P, Q, and R in a true and false, so there are 8 such possible combinations. For each of those combinations, the truth value of P or Q and R equals the truth value of the right hand side, P or Q and P or R, right? And remember this, so this proposition evaluates the true only if these two are equal. So how do you prove that? Well, one option is you could go through each of these 8 possibilities, and for each possibility you check that this and this evaluate to the same, which is fair enough, but you don't need to break it down into the smallest possible cases you can. You can work with more higher or coarser grained cases. So in this case, I'm going to consider only 2 cases instead of 8 cases that are implicit here. And those 2 cases are P or not P. So either P holds or not P holds. So indeed, it's an exhaustive case analysis. So it's important that the cases you consider, their disjunction is true, which is to say at least one of those cases has to hold. You're not overlooking any case, you're not omitting any case. So in this case, those 2 cases are P and not P. And in the case of P, so if P holds, then you have to prove, so remember, you have to show that if case 1, then the statement you're trying to prove is true. So in this case, if case P, then something, right? Then this holds. Well, to show that if P, then something, you can assume P holds. So I'm going to assume P holds. Then let's look at what the left-hand side is. If P is true, then Q and this is true or something. So irrespective of what this is true, right? So P or Q and R, where P is true, is true. What about the right-hand side? It says true or Q and true or R. True or Q is true, and true or R is also true. So in this case, I have true and true, which is also true. So indeed, in this case, the left hand and right hand are equal. So T if and only if T is it holds. All right. So I didn't write that last line there. So therefore, in case P, this proposition holds. In the case of not P, well, if P is false, then this P or Q and R is just Q and R, right? So this is false. P is false. And how about these things here? P is false, so P or Q is just Q, and P or R is just R. So you're left with Q and R. So in this case also you have the same formula on both sides, and irrespective of what value Q or R takes, Q and R, if and only if Q and R holds. Okay, so here I'm again, handling 4 cases of different values of Q or R together. Here also I handle 4 cases of Q and R together. And so the 8 cases were covered by just looking at 2 cases, each of which contained all 4 cases of the other 2 variables Q and R without having to expand them, right? So these 2 cases were proven in somewhat different ways. Here, I showed that left-hand side and right-hand side here are both true. Here I showed that they are both Q and R. So it's, use very different looking arguments in the 2 cases. So that's why it made a lot of sense to split them into 2 different cases for the proof. Here's one last example to show you a little more about some things we do during case analysis. So here is a statement about integers. It says positive integers. It says if a square plus b square plus c square equals d square. So for any ABCD, if whenever this holds, then d is even if and only if ABC are all even. If at least one of ABC is odd, then D is odd, and if all of them are even, then D is even. Right? That's a claim to prove. How do you show this? Well, it's a statement of the form if something, then something. So I start off by saying, okay, suppose these ABCD are such that this holds. Now I need to show that D is even if and only if ABC are all even. Now I'm going to do a case analysis based on, so ABC, each of them could be even or odd. So there are several cases. I'm going to consider a few cases depending on how many of ABC are even. Okay, so the first case is all of ABC are even. And so in each case, I want to show this statement holds, right? D is even if and only if all of ABC are even. So in this case, where all of ABC are even, I want to show that D is even, right? Because this part is true. So if they have to be equal, so then D is even also has to be true. So if ABC are all even, this is an easy case, then a square plus b square plus c square is also even. Each of a square, b square, and c square is even, and their sum is even, and therefore d square is even. Now from d square I can conclude d is even. I will leave it as an exercise that d is, you can prove d is even if and only if d square is even. Just like and if d is odd, if and only if d square is odd. Okay, so d square is even in particular implies d is even. So that is case 1. We're good with that. How about case 2? So my second case I'm going to consider is that not all 3 are even. Instead, exactly 2 of ABC are even and 1 of them is odd. So this case in turn consists of 3 different cases, right? One case is where A is odd and BC are even. Another case is where B is odd and AC are even, and C is odd and AB are even. So there are 3 different cases. But my proof is going to treat all these cases very similar to each other. So here is a trick we will do, or here is a little flexibility we allow ourselves. We'll say, okay, I'm going to only consider one of those 3 subcases, namely A is odd and B and C are both even. And the other cases are going to look exactly the same. I'm just going to save ourselves some space and time by omitting that, but it's exactly going to be the same kind of argument. So in this case, we would say without loss of generality, let A be odd and BC be even. The implication being that this is not the only case. There are other cases, but they are as good as this by renaming ABC if you want. So one way or the other, you can map those are the subcases to this particular subcase. So that's why this subcase is without loss of generality. Okay, so once you fix that, you're saying, okay, now I'm in this subcase where A is odd and B and C are both even. So A is, I can write it as 2x plus 1 for some integer x, and B and C are 2y and 2z. And I expand A square plus B square plus C square, and this is the expression I get for their sum, which is supposed to be D square. And that expression is odd, so I conclude that D square is odd, right? It's 2 times something plus 1, so it's odd. And again, D is odd if and only if D square is odd. So in particular, D square is odd implies D is odd. So in this case, I've shown this, namely D is actually odd, this is false, but so is this. A, B, C are all even is also false in this case. So this case is also, so the proposition holds. The next case is a slightly trickier one. So here exactly one of them is even and 2 of them are odd. Again, without loss of generality, I'm going to take, say, A and B as odd and C as even. And when I expand, I don't get a D square which is odd like I did here. Instead, I get a D square which is even, but it looks like this. It's 4 times something plus 2. Again, I'm claiming that that's a contradiction. So D square, D square is even, no good for us to conclude that D is odd, right? But here, D square is not just, D square is not just supposed to be even. It's if D is even, D square is a multiple of 4. And if D is odd, then D square is odd. So you can never have D square be even but not a multiple of 4. So that's what this is saying here. D square is supposed to be even but not a multiple of 4. It leaves a remainder of 2 when you divide by 4. So it's not a multiple of 4. So this is a contradiction. Such a D square, such a number cannot be D square. It's kind of a even number which is not a multiple of 4 cannot be square of anything, any integer. So this is an impossible case. So in this case, we reached a contradiction, right? So it convinces yourself, that this is a contradiction. I've reached something which is false, and therefore this case is also taken care of. So even though in this case I didn't show that these two things are equal, instead of what I showed is that this case cannot occur. Okay, and that is also good enough. And then I'm left with the last case, and this is analogous to the case 2 where all 3 are odd, in which case D square comes out to be odd. Okay, so in this case also I've shown that this is false because D is odd, and this is also false because A, B, C are not or even. So my case analysis involved 4 cases, of which one case so in 3 cases I showed that this proposition holds, and one case led to a contradiction saying that this case cannot occur. So in fact, I could have, if I knew this ahead of time, I would have said I have only 3 cases, case 1 or case 2 or case 4. But I didn't, I wouldn't see that case 3 is impossible until I look into it. So I might as well consider case 3 as a possibility until I see that it's a contradiction. All right, so that's an example of proof by cases, and you can creatively combine all these techniques and more when you carry out various proofs.